Okay. If we had the longest title award, we'll probably win it hands down. This is the work of my graduate student, David Brickler, who unfortunately could not be here today. Our work is on perception-action coordination, and which is defined as the circular transfer of information between sensory systems and motor structures. And we are prescribing to an ecological approach to perception coined by J.J. Gibson, where perception-action coupling is two sides of the same coin, where the sensory information leads to affordances and action capabilities, and the effects of those actions by an actor then allows for the actor to recalibrate to that information and perform subsequent actions. So we are actually studying near-field applications, which are important for applications such as surgical simulation, mechanical skills trainers, such as the work that was presented by my student last year on near-field perception-action coordination in learning, and also other such similar simulations. So what has been done with regard to perception-action coordination and studying it in virtual reality? Gretchen et al. In 2014 conducted a study to explore perception of dynamic affordances in medium-field VR through a gate that closes at random frequencies and where you have to get onto a gap, a moving gap. And we actually found that natural walking resulted in differences in perception-action coordination in medium field as compared to indirect joystick-based travel. Ibrahimi et al. Studied visual and haptic feedback on virtual reaching task, and they actually found that when you're placing a round peg in a round hole kind of task, maximum acceleration, velocity, path length, and accuracy of reaching to a target was different when participants had visual feedback only as compared to visual and haptic feedback or haptic feedback only. And more recently, last year, Bhargava et al. Compared applications in an interaction fidelity continuum on near-field bimanual psychomotor skills learning, and they found that in the low fidelity and the high fidelity condition, psychomotor skills learning was more efficient as compared to the mid-fidelity conditions. So what's actually missing in the literature? So what we investigated is basically we filled a hole in the literature that has to do with studying the effects of stereoscopic viewing, haptic feedback, visual proprioceptive congruence versus mismatch, and calibration all in one apparatus when it comes to near-field perception-action coordination in a fine motor task. And with regard to task, we actually chose to replicate the pick-and-place task from the Fundamentals of Laparoscopic Surgery curriculum, and that's actually shown on the image on the left, and this was replicated in the virtual world on the right. Our apparatus actually consists of the following. These are the hardware components and the software components. We use Unity to simulate our experimental simulation. Phantom Omni was used for interaction, Open Haptics library, and a 75-inch 1080p time multiplex active stereoscopic display was used to render the graphics. Microsoft Connect was used to induce motion parallax in the simulation. These are the dimensions of our interaction scenario. The pegs themselves were 1 centimeter in diameter. And the center peg distance is 6 centimeters. And the inner diameter of the ring that had to be manipulated from one peg to another was 3 centimeters. We had 3 different scenarios that were presented in random order to the participant, a 3-peg, 5-peg, and 7-peg scenario. The interesting aspect of these scenarios is that in the 3-peg simulation, the virtual end effector moved in a 1-to-1 fashion with the physical end effector, and the proprioceptive, kinesthetic, and haptic feedback all matched. And the 5-peg scenario actually simulates a pick-and-place tasks that mimics a common situation in haptic simulations where there's a gain that's applied to the haptic manipulator's motions in the virtual world in order to maximize the haptic workspace, because the haptic workspace is quite small. So here, the 5-peg scenario, the physical end effector movements are mismatched with the virtual end effector in a 1-to-2 fashion, and the visual feedback is mismatched with the proprioceptive and kinesthetic information. In the 7-peg scenario, the mismatch is exacerbated, where the physical end effector movements are mismatched with the virtual end effector movements in a 1-to-3 fashion, 1 centimeter to 3 centimeter, and the visual feedback is greatly mismatched with the proprioceptive and kinesthetic information. So the kinds of data that we recorded with regard to participants' performance, participants received 20 trials in each of these conditions in a random order. And we measured the completion time, the manipulated object distance or the path length, the number of collisions with the pegs and the ring, as well as the placement error when the ring was placed around the pegs. Our key research questions that guided our research was how do haptic feedback and stereoscopic viewing affect near-field perception-action coordination? To what extent does visual proprioceptive mismatch affect near-field fine motor task performance? And finally, to what extent the above three cues affect calibration or adaptation, or to what extent does calibration adaptation mediate, moderate the task performance? And these were our guiding hypotheses. Independent variables were, the between subjects variables were haptic feedback and stereoscopic viewing. In essence, it was essentially a 2x2 multifactorial study. And the sensory motor congruence mismatch conditions were 3-peg and 5-peg. And we also looked at the sets of trials in order to see a calibration effect. So we divided 20 trials into 4 sets of 5, and then we looked at performance across those sets of trials. There were 40 participants that were recruited. The flow of the experiment consists of the informed consent process. We also examined participants' spatial abilities. And then for training, they had a very small training task in which they had to place a ball in a bucket for 10 trials. And then the random order of 3-peg, 5-peg, and 7-peg scenarios were presented to the participant. So let's look at the results. With regard to completion time or the efficiency of the task performance, we found a main effect of haptics, as well as the main effect of the gain scenarios. So time per trial was significantly higher in each of the gain scenarios when the haptic feedback was turned off as compared to when the haptic feedback was turned on. We also found a main effect of trial sets where there's evidence of visual motor recalibration, in which the mean time per trial was also significantly higher in the first trial set as compared to the second, third, and fourth, but in both conditions, with and without the haptic feedback. When we look at the efficiency of the motion with regard to the manipulated object path lengths were significantly higher when haptic feedback was, haptic and stereo were both off as compared to when haptic and stereo were both on. So that is unsurprising. However, what was surprising to us is that when one or the other was present, but not both, they were not significantly higher or lower than the other. So performance with regard to the efficiency of the manipulated object motion was similar. Again, with regard to the economy of motion of the manipulated object, we found that there was an interaction effect between the gain scenarios that were presented and stereoscopic viewing. Interestingly, only the visual proprioceptive kinesthetic discrepant scenarios, the 5-peg and the 7-peg, the ring distance was significantly higher when stereo was absent as compared to when stereo was present, but not in the congruence scenario. Again, we also found an interaction effect with regard to ring distance with stereo by trial sets. There was evidence of perceptual motor calibration found only in the condition when stereo was absent, such as participants significantly adapted their economy of motion from the manipulated object from the first trial set to the rest of the trial sets when stereo was absent, but then when stereo was present, they seemed to be well adapted already. Also, with regard to number of collisions, we found a main effect of haptics and stereo and the number of collisions with regard to effectiveness of task performance. Unsurprisingly, the highest number of collisions were when haptics and stereo was off, and the least collisions were when stereo and haptics were both on. However, interestingly, there was no difference between the mean number of collisions when either one was absent but not the other. Also, we found, additionally, when haptics was off, we found that there was that the number of collisions in the 7-peg scenario was significantly higher than the 5-peg and the 3-peg, and they were all significantly different from one another when haptics was off. However, when haptics was present, only the congruent scenario was significantly different or lower than the divergent 5-peg and 7-peg scenarios. And there was no difference between the 5-peg and 7-peg when haptics was on. Finally, we looked at placement error of the ring around the pegs, and we found the main effect of stereo, wherein when mean placement error was significantly higher when stereo was absent as compared to when stereo was present. No other main effects of haptics or the gain scenario or interaction effects were found when it came to mean placement error. So let's look at what we actually discovered with regard to the guiding hypotheses that helped us answer our research questions. One of our first hypotheses was that when haptics and stereo were both enabled, this will improve task performance. This was supported. Haptics and stereo were shown to influence most of the dependent variables, our measures that we studied, however, in different ways. So haptics improved the efficiency of task performance as well as the economy of motion, i.e. time and distance, and stereo improved the economy of motion distance as well as the task performance variables such as the mean number of collisions and the placement error. And our second hypothesis was that participants' performance is expected to be best in the one-to-one congruence scenario as compared to the discrepant 5-peg and 7-peg scenarios. And this was supported. Adding discrepancy was shown to have an effect of time efficiency, economy of motion distance, as well as our performance variables, collision and placement error. Stereoscopic viewing seems to influence the economy of motion in the visual proprioceptive discrepant 5-peg and 7-peg scenarios, and the magnitude of the mean number of collisions between the discrepancy scenarios was larger when without haptic feedback than when haptic feedback was present. Finally, a third hypothesis that motivated us was that participants' performance is expected to gradually improve from the first trial set to the last. And this is congruent with a lot of research that's been done on visual motor recalibration in medium field and other near field tasks. And this was somewhat supported with regard to completion time, efficiency of the task performance, and ring distance, economy of motion. Performance was poorer in the first trial set, but in every other trial set it was significantly better. And with regards to economy of motion, participants seem to be relatively well calibrated in the presence of haptics as compared to in the absence of haptics. In the absence of haptics, within the first 10 trials, they seem to adapt and calibrate. So finally, with regard to some conclusions, haptics and stereo seems to differentially affect performance characteristics. We found that when it comes to near-field perception-action coordination, haptics has a stronger influence on efficiency, while stereoscopic viewing has a stronger influence on economy of motion and task performance. We found a negative effect of visual haptic discrepancy on user performance. The discrepant scenario exaggerates the gap we found in performance between the presence and haptics, absence of haptics and stereo. That is, it exacerbates it when you have reduced Q conditions. And the users tended to adapt their perception-action coordination rapidly, we found, when there is an opportunity to do so within 5 to 10 trials. So we have some recommendations for the near-field application developers that use haptics in applications like surgical simulation and others. And many near-field fine motor haptic simulations included simulated robotic assisted surgery, for example. A gain is sometimes added to maximize the haptic workspace. And we have found that this mismatch in visual haptic proprioceptive feedback can degrade efficiency and effectiveness of task performance. However, in spite of these reduced Q situations, participants tend to calibrate or adapt their near-field perceptual motor coordination within the first 10 trials. So when possible, it is recommended that application developers have some sort of a near-field fine motor, some sort of an acclimation phase or a training phase in these near-field fine motor simulations. Our future work is we hope to compare large-screen immersive display viewing simulations when it comes to near-field perception-action coordination as compared to head-mounted display. The reason for that is that in the LSID condition, large-screen immersive display condition, the virtual setup cannot be perfectly co-located with the physical setup. Because of the minimal depth plane, there is an offset between the physical end effector and the virtual end effector, which is not present when participants view the same scenario in a head-mounted display condition. So it's interesting to study that. But also, what's also interesting is in head-mounted display situations, without a self-avatar hand at least, there is the absence of proprioceptive information that could also degrade near-field perception-action coordination and motor control. And we want to study that more rigorously in future studies. So this is the work of my student, David Brickler, who unfortunately couldn't be here. He's the corresponding author, but you're also welcome to approach me if you have any questions. Thank you.
Great. Great talk, very interesting work. And we have time for maybe one or two questions. My first question would be the pick and place test that you showed at the start, was it 2D grid? Why did you decide to go with a 1D grid?
The pick and place task was essentially a one-dimensional grid because we were trying to work with the longitudinal haptic workspace that was available to us with the Phantom Omni. We weren't trying to exactly in a one-to-one match replicate the FLS training scenario, which does simulate the transfer of the manipulated object laterally as well as longitudinally. So in future work, we would like to do that.
Thanks, Ab, for this work. Could you talk a little bit about, so you used a stylus-based approach. How do you think this affects whole hand interaction as opposed to just a point-based interaction?
That's a very, very interesting question. I think we were limited by the technology that we were using when it comes to a stylus-based approach, and we were also inspired by the laparoscopic simulators that essentially uses a stylus-based approach. If you look at the box simulators that are out there, or the medium fidelity simulators for laparoscopic training, they use a stylus-based approach. And in terms of affordances, it matches that of the laparoscope. With regard to fine motor actions of being able to pick and place the object via finger-based actions, and to what extent haptic feedback is important is an open question. And we would love to study that in the future if we had the opportunity to do so. Sorry, I don't have a good answer for you.
Bruce Thomas, University of South Australia. This is just a bit about your experimental. Oh, great study, thank you. You chose to increase the complexity of the task from 3 poles to 5 poles to 7 poles. You could have just moved the 3 poles farther apart. I was wondering if the complexity of the task, did you feel that had an impact on the results?
True. So now it may have, but what we wanted to study was basically the trade-off between manipulating the center-to-center distance between the pegs, yep, or keeping that constant from one scenario to another, while manipulating or adding a gain to your virtual end effector that's either congruent or divergent with your physical end effector. So if we feel that the results should be similar, because if you're moving the manipulated object from one peg to another, and you're increasing the distance, the center-to-center peg distance between the pegs, it's the same thing as perhaps moving the object from, say, the first peg to the last peg in the 7-peg scenario.
Yeah, no, good.
Great. Thanks, Ab, again.
Thank you.